Okay, so let's start the lecture for today. Okay, so we've been talking about non-homogeneous equations. Okay, so and here is a small short review of what we have been doing in this area of non-homogeneous equations. Okay, so suppose you want to solve this equation: y double prime plus pt of y prime plus qt of y is g of t. So there are three major steps from which you are able to solve this equation. The first step is that you should find a complementary solution. So complementary solution means that you want to replace the g of t by 0 on the right hand side. So as long as you replace everything by the g of t by 0, the solution to this homogeneous equation is what we call the complementary solution. Okay, so the complementary solution. Now, as long as you have the complementary solution, you just want to find a particular solution of the non-homogeneous problem. Remember, here is a particular solution, is not of the homogeneous problem, but it's a particular solution for the non-homogeneous problem. That means this particular solution satisfies the non-homogeneous equation with the g of t as the right-hand side. Okay, so as long as you have both the complementary solution and the particular solution, you should add them. Okay, so you add these two parts of the solution. That's going to give you a general solution of the non-homogeneous equation. Okay, so that's kind of the general principle how you're going to solve a non-homogeneous second-order equation. Okay, so now we know how do we do the step 1 and step 3, right? So you know the complementary solution. For example, it can be derived from the characteristic equation theory, right? So the method of characteristic equation. So that's kind of good. Okay, so you know how to do this. Now the only problem left is that you don't know how to find a particular solution, right? So particular solution in particular to the non-homogeneous problem. It's not to the homogeneous problem, but to the non-homogeneous problem. You don't know how to find it. So last time we lectured, we have been talking about an important method that's called method of undetermined coefficient, right? So what's the method of undetermined coefficient? It works for 3 special types of functions only, like the right-hand side. What I'm saying is that the 3 special types of the right-hand side g of t. For example, if the g of t is an exponential function, you should try an exponential function. If the g of t is a trigonometric function, right? So, and then you should try a combination of sine and cosine. So that's our principle. That if you have an exponential, you just try one exponential function with the same exponent. But if it's a sine and cosine, you should try a linear combination of sine and cosine. And if it is a polynomial, you should try a polynomial of the same order. That's important, same order, right? So that's kind of the thing we talked about for last lecture, right? So here as a warm-up, okay, so as a warm-up, let's look at some examples that we are left with for last lecture, okay? So for example, this one, right? So this one says you want to have y double prime minus 3 times y prime minus 4y is equal to an exponential multiplied by trigonometry, right? So it's an exponential multiplied by the trigonometry. What kind of complementary, I mean, we know the complementary solution just by setting this to 0, so that's, I will skip it, okay? So that's not complicated. But how do you try a particular solution? Well, we know that the particular solution should be an exponential function multiplied by a combination of sine and cosine. So that means, I mean, this is what we call it divide and conquer principle. So that means the right-hand side, the complementary solution should, the particular solution should be exponential of t multiplied by linear combination of sine and cosine. So the next thing is that you should take derivatives of this function. And I was skipping this last time, but I think it's important. Okay, so what happened here is that you have to do careful calculations, right? So you have to do very careful calculations, right? So do not try to skip anything in the calculation, but this is required on the exams, right? So let's say y of t is a times e power t of cosinuses of t, right? Cosine 2t plus b times e power t of sine 2t, right? So cosine 2t and sine 2t, right? So cosine 2t, sine 2t. That means you have to take derivatives. So y prime of t is, so here your derivative should be taken with respect to product rule, right? So it's a product rule. So you should take a derivative with respect to this product rule. So that's a e power t of cosinuses of 2t, and then minus b e, so this is still a, right? So minus the a, right? So a e power t, right? So, and cosine 2t derivative is sine 2t, but you have to multiply by 2. Cosine derivative is a negative sign. Then you're going to have b e power t sine, right? So it's b e power t of sinuses of 2t, right? So sine of 2t, and then plus 2b e power t, sine derivative is cosine, so cosine 2t. So that's y prime is actually, you have to collect the terms. So by collecting terms, you see e power cosine 2t, e power cosine 2t is a common term. So that's a plus 2b e power t cosine 2t. And then here as plus, okay, so b minus 2a, because this is b minus 2a, with this common term, e power t sine 2t. So you have this, right? So that's y prime of t. And you have to keep taking derivatives. So y double prime of t. So this here, you can see that the very important thing is that you have to be very patient with this calculation and do not make errors, right? So if you are not so patient, then you might lose on this battle, right? So let's say you're not going to get enough credit for the problem. So you have to be very patient, and it's not very hard. So it's actually a plus 2b, right? So you're going to have e power t cosine 2t, and same rationale, that's going to be minus of 2 times a plus 2b e power t sine 2t, right? So cosine derivative sine. And then it's plus b minus 2 times a of e power t sine 2t. And then it's a sine derivative cosine, so that's plus 2 times b minus 2 times a e power t cosine 2t. So you're going to have this. And you, as long as you have this, you collect the e power t, right? So that's a plus 2b plus 2b minus 4a. So it's minus 3 times a plus 4 times b, right? So multiply by e power t cosine 2t. And then here is b, so it's minus 2a, so plus minus 4 times a. And then there's a minus 4 times b plus b, so minus 3 times b of e power t sine 2t. So you're going to have this, right? So that's all the derivatives that you want to have, right? So you want to have. So that means you have to collect all these terms. So that will be a much easier task. You collect the y double prime minus 3 times y prime minus 4 times y. So you can see that these terms are linear combinations of two terms, e power cosine 2t and e power sine 2t. So you collect this, just collect the coefficients, right? So that means this term minus 3 times this term and minus 4 times this term. So that's kind of what happened here. And the same thing for the sine, right? So for the sine, and you connect everything, you're going to see that after calculations, it's minus 10a minus 2b and minus 2a minus plus 2a minus 10b is equal to what you're given. And therefore, from which you can solve for a and b. Okay, so here is just as a warm-up. Okay, so as a warm-up, just to take you a few minutes to see that the last example that we showed in undetermined coefficients, how it is calculated, right? So basically, we can say that it is calculated from patience, right? So you just have to be patient and do all the calculations, and you should be fine. Okay, so that's kind of the thing. Okay, so that's kind of the thing. So that's what we want to have for the method of undetermined coefficients. Okay, so now today's lecture, we're going to talk about another method called the variational parameters. Okay, so that's today's lecture. We're going to talk about variational parameters. Okay, so variational parameter is very another method of finding particular solutions. So these are first of all, both methods are used to find particular solutions. Okay, so that's very important. So what's the variational parameters going to do? Okay, so you're looking for y double prime plus pt of y prime plus qt of y is equal to g of t. So this is a non-homogeneous problem, right? So non-homogeneous problem. And you would like to say that the homogeneous part, okay? So the homogeneous part consists of the so-called complementary solutions, right? So homogeneous part consists of the so-called complementary solutions. Right, so complementary equation. Now, complementary solution must take the form yct is c1y1 of t plus c2y2 of t, as we learned in our previous lectures. The y1 and y2 are the so-called fundamental solutions, right? So, and fundamental solutions means that the y1 and y2 is going to form a so-called Wronskian. Wronskian means that the first row are the functions, second row are the derivatives. The Wronskian is non-zero, right? So the Wronskian is a function of t, has to be non-zero. That means y1, y2 form a set of fundamental solutions. As long as you have the fundamental solutions, you do linear combination of fundamental solutions are going to give you complementary solution. It's not going to give you particular solution, right? So it's complementary means that the right-hand side is actually equal to 0. How do you find a particular solution? Okay, so how do you find a particular solution from the complementary solution? Suppose you know the complementary solution. I want to find a particular solution. So by variation of parameters, sometimes it's also called variation of constants. Okay, so variation of constant or variation of parameters means the following. Okay, so if you look at the complementary equation, okay, so if you look at the complementary equation, the two fundamental solutions are multiplied by some respective constants, respectively, right? So they are multiplied by some constants, respectively. Now, by variation of parameters, it means that you would like to try a particular solution that varies these constants. So that means u1t, y1t plus u2t of y2t. So that's what we call variation of parameters. So it does vary in the sense that it is going to vary those constants into functions of t. You vary the constants, here are the constants, but you vary them into functions of t. That's the essence of variation of parameters. So maybe I'll draw an arrow here and an arrow here, right? So just to show that this is a variation of parameters. You're varying the parameter, right? So let me make my board work. Okay, so look better. Okay, so let me write the Wronskian somewhere else so that these arrows look better. Okay, so they're better aligned. Okay, so that means that I want to have the Wronskian. So the Wronskian is written, let's say the Wronskian. Okay, so Wronskian W of y1 and y2 is equal to the determinant y1, y2, and y1 prime, y2 prime. This has to be non-zero. But then it's this correspondency. Okay, so the correspondency here are called variation. Okay, so variation of constants. Why we call variation constant? Because you are varying the constants. There are constants in front of the fundamental solutions. You are varying the constants into functions of t. You are varying the constants into functions of t, and that will give you a shape of the particular solution. But there is a problem here, right? So there's an immediate problem here that you actually don't know what is u1, u2. You just know the form, right? So one should say that we just know the form of the solution has to be in the form of a combination of y1 and y2. Remember, the y1 and y2 are the fundamental solutions of the complementary equation. It's not for the non-homogeneous one, but homogeneous one. And with the Wronskian is non-zero. So that's y1, y2. But you have varied in the constants. Previously, it was two constants, c1 and c2. Now you varied them into two functions, u1t and u2t. So therefore, you have to know how these functions look like. Otherwise, you're not finding a particular solution. You're only finding it like a form of the particular solution, but you don't know exactly what will be the particular solution. Okay, so that kind of important thing is this variation of parameter method. Okay, so variation of parameter method. So how to do that? Well, here I will give you some hints to memorize these formulas. That will be very important for you to understand this lecture. Okay, so to understand this lecture, so that's kind of formulas that help you to understand them. But I would like to remind you that our course is not going to give you these formulas on exams, but rather you have to memorize these formulas just by yourself. Okay, so that's kind of very important. So what we are facing is like the non-homogeneous equation, right? So what we are facing is like non-homogeneous equation, y double prime plus pt of y prime plus qt of y is equal to g of t. That's the non-homogeneous equation. Now, you want to first do the complementary equation. Okay, so, right, so you're first doing the complementary equation, yc double prime plus pt yc prime plus qt yc is equal to 0. So that's the complementary equation. Now, with the complementary equation at hand, you find the fundamental solutions. Okay, so you find fundamental solutions. So fundamental solution is given by yc of t, cy y1 of t plus c2 y2 of t, where the y2, so this is not fundamental solution. So to be more precise, I should say fundamental solutions are the solutions y1 of t and y2 of t. They are solutions of the complementary equation, and they satisfy the Wronskian of w of y1, y2 is equal to y1, y2, y1 prime, and y2 prime. This guy has to be non-zero, right? So the Wronskian is something that has to be non-zero, right? So you have this. Now, as long as you have this, you're going to have the complementary solution. Complementary solution yc of t is like c1 y1 of t plus c2 y2 of t, right? So, and then by variation of parameters, so it means that particular solution via variation of parameters. So I will write v of p is going to give you like the particular solution is u1 of t, y1 of t plus u2 of t, y2 of t. So that's kind of you varying those constants into functions. Now the point here is how do you calculate u1, u2? So that's the problem, right? So now I give you a formula. Okay, so u1 of t is going to the integral from the t0 to t minus y2. Okay, so multiplied by g. Okay, so y2 multiplied by g of s divided by the Wronskian y1, y2 of s ds. And then I'm going to say that u2 of t is equal to the integral from t0 to t of y1 of s multiplied by g of s divided by the Wronskian y1, y2 of s ds. Okay, so that's kind of the formulas that that can help you to calculate the u1, u2. Okay, so that's a very important formulas. Now, how to memorize this formula? So that's a key point, right? So as I said, these formulas are not really going to be given to you as forms, right? So as appendix formulas on exams, but you have to memorize them. So how do you memorize them? Well, first thing that remember, the Wronskian is non-zero, right? So we know that the Wronskian is not going to be 0. So if you have something on non-zero, it means that it's on a denominator. So you won't put the Wronskian on the numerator because you remember, Wronskian has to be non-zero. Is that good for everybody? Okay, so the non-zero thing must be on a denominator, and you can see that both u1 and u2 has the Wronskian as the common denominator. So that's not a problem. Just remember, the Wronskian is non-zero, and therefore this non-zero object has to be on a denominator. You won't make any mistakes. Okay, so that's kind of one, the first simple remark. The second simple remark is that we're looking for a particular solution of the non-homogeneous problem. Now, everything about the homogeneous problem, in a sense, is being incorporated, right? So all the information about the homogeneous problem is incorporated into the two fundamental solutions, y1, y2, because these two fundamental solutions help you to, as a building blocks, help you to build up the complementary solution. So therefore, all the information about the homogeneous equation, which means that it is the information on the left-hand side of this equation. Remember, homogeneous equation means that the right-hand side is 0. Everything is about the left-hand side. So all the information for the left-hand side are contained in the y1 and y2. Right? So therefore, if you want to build up a non-homogeneous solution like capital Y via the variational parameters, then the U1, U2 must somewhere contain the non-homogeneous term. Otherwise, you have no information about the non-homogeneous term being used here, which is not kind of a information conservative. You want to have something that is information conservative. That means all the information plugged in are being used as information provided in the output. So that's what you want to really have. Okay, so that's what you really want to have in this statement here. Okay, so that's kind of the thing. So if you want to have that, okay, so if you want to have that, then it is natural. Okay, so it is natural that you want to have the g of s on the multiplicative as a multiplicative factor on both u1 and u2. So g of s must stay there. Okay, g of s is just the g of t, and therefore the only thing you remember is that u1. Okay, so u1 is corresponding to minus y2. Okay, so it's corresponding to minus y2, and u2 is corresponding to plus y1. Okay, u2 is corresponding to plus y1. So that's kind of the slogan. Okay, so the slogan here is that u1 is corresponding to minus y2, and u2 is corresponding to plus y1. So you can see that there's actually a flip here. u2 is not corresponding to y2, u1 is not corresponding to y1, but you have to flip. u1 is y2 with a minus sign here, and u2 is y1. So that's kind of the slogan for today's lecture. Can be summarized very simply as the following slogan. So u1 is y2, and u1 is minus y2, and u2 is plus y1. So you can simply summarize the slogan of today's lecture as such a slogan. The good favorite, u1 is minus y2, u2 is plus y1. So let's look at this formula any better. Okay, so u1 is minus y2, and u2 is a plus y1. Okay, plus y1. But what's the integral about? Well, the integral is from t0 to t, where that's kind of for a kind of initial value problem. So that means you have to give me y t0 and y prime of t0. Okay, so is something, and that's kind of related to t0. But it is kind of natural to see that even if, okay, so even if I say that, okay, so even if I say that u1 of t, okay, so is the integral of minus y2 of t, okay, so of g of t divided by the Wronskian of wy1, y2 of t. Remember, here just one small remark, that the Wronskian is a function, right? So you take the Wronskian is actually evaluated at some point at t, where you take function values as well as the derivatives at that function value. So it's a function of t. So it's safe to use this function dt, and then I'm going to consider u2 of t is the integral of y1 of t multiplied by g of t divided by the Wronskian of y1, y2 of t dt. So that's kind of the thing, right? So now here, these integrals are without the integrating domains. I mean, it's not without this where you start and where you stop. Why is that the case? Well, these are antiderivatives. So the antiderivatives means that u1, u2 are just determined up to some unknown constant c1 and c2. So these are antiderivatives. Now, if you use that antiderivatives to build your particular solution, you're going to see that, for example, it will be u1t plus some c1 multiplied by y1 plus u2 of t plus some c2 multiplied by y2. And if that is the case, then you're going to see u1t y1 plus u2t y2 plus c1 y1 plus c2 y2. So that's the problem. If the u1t and u2t are being altered by some constants, then the particular solution is just the changes up to a complementary solution. Is a good fabric, right? So the particular solution just changes by a complementary solution, which means that this particular solution is another particular solution plus one of the complementary solutions. Is a good family, right? So, and this will not affect your general solution. Remember, the general solution is going to be built. The general solution of this problem is going to be built as the complementary solution plus the particular solution. If the particular solution changes by a complementary solution, then this complementary solution is going to be absorbed into the complementary solution here, because the complementary solution is actually undetermined. It is determined up to those constants, right? So as long as you have this, it means that your solution, okay, so your solution so obtained is still a form of the general solution. I mean, it's just with different constants. The constants might change because you're changing it by another complementary solution. Is a good family? Okay, so that's kind of the very important. Okay, so that's kind of the very important thing here is that I mean it's a good news, because it tells us that previously you probably have to be worried about the integral domains, where you start integral, where you end integral, and that will affect your calculation of the integral. But now it's after this argument, it is becoming clear that you don't have to do anything. You just have to calculate minus y2 multiplied by g divided by Wronskian plus y1 multiplied by g divided by Wronskian. You calculate the antiderivatives. As long as you have the antiderivatives, no matter what functions they are, you put these antiderivatives back into this, this variational parameter formula, you obtain particular solution. And you use that particular solution as well as the complementary solution, you add together, that's a general solution. As long as you have the general solution, you can try to see what are the constants. Is a good family, right? So that's kind of a simple task, right? So that's kind of a simple task. Okay, so that's kind of a simple task. So that's kind of the information about this U1, U2 that we like to talk about. Okay, so that's kind of let's look at this theorem. Okay, so the theorem says that if the functions, okay, so there are some conditions like P, Q, G are continuous. Okay, so plus, plus, plus. And then you have to see that a particular solution of the non-homogeneous equation where the right-hand side is G is given by U1 plus multiplied by Y1, U2 multiplied by Y2, where U1 is a minus Y2, so minus Y2, U2 is plus Y1, both are multiplied by the G divided by the Wronskian. Is a good family? Okay, so that's kind of a very important formula. Now with this formula at hand, it means this particular solution theory via the variation of constants is complete. You can just use these two formulas as the coefficients in front of those y1, y2 to build a particular solution. Okay, so that's kind of very simple business. Here, the Wronskian is a determinant. So that's y1, y2 prime minus y2, y1 prime. Okay, so that's kind of the thing. Okay, so here I want to make a remark which we already made, is that you can compute an indefinite integral instead of the definite one, because you're not really worried about those constants being added to U1, U2. It will just alter the particular solution by a complementary part. So you don't worry about this. So that means it's enough to calculate the antiderivatives and choose the constant in the result to be, I mean, you choose any constant you like. Usually we like to choose 0. I mean, as simple as you can. Okay, so that's kind of principle. But here there are actually two more remarks I like to make. The first thing is that the method of variation of parameter is more general than the undetermined coefficients. Why? Because here the formulas are very general. No matter what you have for the G, you can always use this G to multiply what you want and you integrate. So no matter what kind of G you have, you can always do that. It's a good favorite. But previously, as we just see at the beginning review of today's lecture, as we just see that the method of undetermined coefficients only works for either exponential or sine, cosine, or polynomial, or maybe combinations of them. It doesn't work for any other types of right-hand side. But the method of variation of parameters works for any right-hand side. No matter what you like, you can use it. Is a good family? Okay, so that's kind of a very important thing, is that method of variation of parameter is like a fatal and fundamental and final method. So it works for any arbitrary shape of the right-hand side G of t. Is a good family? Okay, So however, I want to make one final remark that you might not have noticed, but it will be very important for our later lectures. We will see some examples demonstrating this effect. Namely, when we say g of t, the equation is in a standard form. Right, so when I start to write this equation, remember, this equation is in a standard form. So let me use red ink. Right, so when we write this equation is already in a standard form. So that's very important. The coefficient in front of the second derivative is 1. And if you're not in a standard form, what kind of problem you are going to have? So let's look at this issue. Okay, so let's say the equation in a standard form. The equation in a standard form has the shape y double prime plus pt of y prime plus qt of y is equal to g of t, the standard form. And you want to try a particular solution of the shape u1 of t, y1 of t, plus u2 of t, y2 of t. And you know that the formula u1 of t in general is the antiderivative of minus y2 multiplied by the g divided by the Wronskian of y1, y2. I'll write it simply. And the u2 of t is equal to the integral of y1 of g divided by the Wronskian between y1 and y2. So that's what you want to write. But if the equation is not in a standard form, so not in standard form, suppose the equation is not in a standard form, right? So then it might look like, for example, 2 times y double prime plus, let's say, another pt. Okay, so y prime, I will still use pt. Okay, qt of y prime, y is equal to g of t. Suppose it's not in a standard form. Then are you going to use the u1 of t as before? Well, if you use that u1 of t, you're going to start have problems. Why? Because w, the Wronskian, right? So u2 of t is equal to the integral of y1 of g divided by w, y1, y2. So suppose you use this as your particular solution. Then you can see that this equation is not in a standard form. So that means it will correspond to a standard form of this equation, y plus pt over 2 of y prime plus qt over 2 of y is equal to gt over 2. Right, so you can divide by 2 in order to turn this equation in standard form. If it is divided by 2, then it means that here you have to also replace the g by g over 2. So you reach a confusion here. Because you don't have a unique choice of g, it really depends on the coefficient here, which in a standard form. So that's very important, is that you must turn the equation in standard form first before you apply those formulas. So these formulas, so basically these are not correct. So it's not correct simply because the equation is not in a standard form. So do not use, okay, so do not use this theory like arbitrarily. When the situation is not in a standard form, you simply don't use it. So what happens here is that no matter what equation you're given, you can always turn it into a standard form equation first by dividing both sides of the leading coefficient of the double derivative. That makes the leading coefficient to be 1. Your equation is standard form. As long as in the standard form, you have a unique choice of the g. You won't have the g or g over 2. You won't be bothered with this non-uniqueness. But you're going to have a unique choice of the g of t that you put it into the formula for u1, u2, you produce the right solution. Otherwise, you are going to make mistakes. So that's why we emphasize a lot on standard forms of this equation again and again during these lectures, because you really need the equation to be in a standard form in order to apply the right formula. So here, it is very important remark is that the equation must exactly have the standard form. That means the equation leading coefficient must be 1. So that's very, very important. Okay, so you must turn the equation in standard form before you can apply anything. Is that good, family? Okay, so that's kind of all the remarks that I would like to make about this method of variation of parameters. Okay, so the variation of parameters. So here, let me show you an example. Okay, so here's a nice example that was taken from same thing as previous problem, but we are going to use another method, right? So the equation is again y double prime minus 3 times y prime, right? So minus 4 times y is equal to this 3 times e power 2t. So previously, we were using the method of undetermined coefficients to find a particular solution, right? So here we want to find a particular solution so here we want to find a particular solution from the undetermined method of variation of parameters. So that means you should start from the complementary equation, okay? So this is what you're going to do on an exam. So maybe you should write a complementary equation. Okay, so I will not abbreviate, but you can write the full name. Okay, complementary equation is C is equal to 0, and then you solve the complementary equation. So that means r squared minus 3 times r minus 4 is 0. So r minus 4 multiplied by r plus 1 is 0. So that means r1 is equal to 4, r2 is equal to minus 1. So that means you're going to have yc of t is c1 e to the power of 4t plus c2 e to the power of minus t. So that's kind of the complementary equation. Now, the point here, there's another issue here raised when we are trying to solve this problem, is that are you going to set this one to be your y1 of t? Are you going to set this one into my y2 of t? Well, that's a good idea. But what happens if I call this to be y2, I call this to be y1 and switch the two? Well, what is going to happen? Well, if you do that, it doesn't quite matter, because if you fix, like you switch the y1, y2, then you're going to switch the u1, u2 either, right? So that means your solution won't change. It's just the labeling of 1 and 2 are going to switch. So what I'm trying to convey here is that my hint, my tip for your exam is that stick. Okay, so stick to your choice. Okay, so stick to your own choice throughout. Right, so that means, okay, so let me say, stick to your own choice. So I would say stick to your own choice throughout. So that means you always stick to your own choice. If you choose this to be y1, you choose this to be y2, then you should stick to it. Don't switch during your solutions. If you choose, you have to go through it till the end of the solution. So that's always y1, that's always y2. Well, somebody is going to say, I'm going to say this is y1, this is my y2. Well, that's okay. But if you do that, you have to always stick to your choice till the end of the solution. Is that good for everybody? Okay, so that's just a side remark that do not kind of tacitly switch your choice, right? So you have to always remember where you start. You want to choose this y1, you want to choose this y2, then don't change it. Never try to change it. You have to stick to it. Is that good for everybody? Okay, so that's kind of the same. So here, so a good idea, okay, so a good idea for you to make sure that you don't mess up on your exam is that you should draw an arrow, right? So let's say this is y1, this is my y2. You draw 2 arrows, then you're clear with what your choice of y1, y2. Is that good for everybody? Okay, so now we want to try a particular solution, right? So let's say I want to try a particular solution. So how do I try a particular solution? First of all, remember the formula. It is equal to the variation of constants, u1t, y1t, plus u2t, y2t. So you have to use those constants. And from those constants, so you have to remind, so this is what you're going to do on an exam. Remind yourself of the formulas. This is minus y2 of g divided by the Wronskian of y1 and y2, and u2t is equal to integral of plus y1 of g divided by Wronskian y1, y2. So remind yourself of the formula first. Make sure you memorize it. These two formulas are not going to be provided to you on exams. You're going to be completely out of it, but you have to recover it by yourself. So that's very important. Remember, the slogan is minus y2 and plus y1, and there are some remarks that we have been making throughout these lectures just to make sure that you don't mess it. Is that good? Okay, so that's y1, y2. But what about the g? So before you use the g, you have to first make sure that the equation is in a standard form. So that's kind of very important. You have to make sure that this equation is standard form. So that means the g of t is just 3 times e power 2t. because the equation is already in standard form. If it's not in a standard form, you have to divide both sides by the coefficient in front of the highest derivative to make it into a standard form. So that's very important. Here, there's no problem here because the equation is already in a standard form. So that's your G. So with your G at hand, and remember, you have to calculate the Wronskian then, right? So what are my choices of y1, y2? Well, we have been choosing that y1 of t is e power 4t and y2 of t is e power minus t. As I said, you have to stick to your own choice of your fundamental solutions. You have to stick to your own choice. Do not switch it. This is y1, this is y2. Okay. So once you have this y1, y2, it's easy to calculate the Wronskian of y1, y2. It's going to be e power of 4t. The first row are the functions. The second row are the derivatives, as we explained, right? So that's 4 times e power 4t minus e power minus t. So that's kind of minus e power 4t. So that's kind of minus 4. So minus 5 times e power of 3t. So that's going to be the Wronskian. Is that good, family? Okay. So once you have the Wronskian, you can see that I can calculate u1 of t is the integral of minus y2. What is y2? Well, y2 is what you have so given here, right? So y2 is e power minus t multiplied by the g. G is 3 times e power 2t. So 3 times e power 2t. Now divided by the Wronskian is minus 5 e power 3t. So that's going to give you what? That's going to give you 3 over 5, the integral of e power minus 2t, right? So e power minus 2t. So that's going to give you a solution, right? So that's going to give you a solution, right? So it's minus 10 over 3 over 10. Okay, so minus 3 over 10 e power minus 2t. Maybe plus constants, but we don't need as constant. Remember, this u1 of t and u2 of t can be chosen up to constants, as we explained. So that's going to be your u1 of t. And the same rationale, you can calculate u2 of t, right? So maybe I'll just go a little bit down. Okay, so the same rationale you can calculate u2 of t is plus y1. So y1 is e power of 4t multiplied by 3 times e power of 2t, right? So as a g divided by the Wronskian minus 5 times e power 3t. So that's minus 3 over 5, the integral e power 6t. So e power 3t. So that's going to be minus, okay, 3 over 15 e power 3t. So that's going to be another, okay, so here's, I'm just a moment, okay, so it's e power 60, okay, so, okay, so sorry, that's 1 over 5, okay, so this 3 over 15 is already 1 over 5, right, so that's, I'm actually right, so, but just the calculation can be simplified a little bit, it's 1 over 5. So that's kind of the u1, u2. Is that good, family? Okay, so as long as you have the u1, u2, you're going to have the solution. So the particular solution is equal to the u1. So the u1 is minus 3 over 10 multiplied by e power minus 2t. u1 of t multiplied by y1 of t is e power of 4t. And then plus the u2 is equal to, u2 is equal to here, what I'm choosing is a minus 1 over 5, right? So minus 1 over 5 e power 3t u2 multiplied by y2 of t is e power minus t. So that's e power minus t. So this is actually going to give you 3 over 10 e power 2t minus 1 over 5 e power 2t. So that's kind of 10. So that's kind of minus 2 over 10. So minus 5 over 10, 1 over 2 e power 2t. So that's going to be your particular solution. So you found your particular solution. As long as you have your particular solution, you can see that the general solution, right? So the general solution, y of t is equal to the complementary solution. Complementary solution is found here as c1 e power 4t, c2 e power minus t, right? So plus c2 e power minus t plus the particular solution is actually, right? So the particular solution is actually minus, right? So it's minus 1 over 2 e power of 2t. Is that good for everybody? Okay, so you have the general solution and your particular solution. And this actually agrees with our calculations in our previous lecture. You can go to the video, for example, for the previous lecture, you're going to find this example, and that's the same solution. Is that good for everybody? Okay, so that's kind of a nice application of this method of anti-term variation of variational parameters. Okay, so here I will have another example, which is even better, and I will leave it. Okay, so to our next lecture, just to make sure that we have a warm up at the beginning of the next lecture. So I will leave this example to the next lecture, and then I have to tell you that on my lecture notes, I have been providing you a lot of further examples that uses either, okay, so they use either the variational parameters or undetermined coefficients to find particular solutions as well as the general solutions. Okay, so this you have to, I would strongly urge you to try them before you get familiar with these two methods. Okay, so I will leave this example to the next lecture, at the beginning of next lecture, just for warm-up purposes. Okay, so that's how I want to say. Okay, so for the lecture, but don't try to leave. Okay, so that's what we say for the lecture. Okay, so let me first finish the recording here. Okay, so that's what I want to say for this lecture.